Latency and resource utilization. More generally, you can think of variable delays as a consequence of dynamic resource partitioning. Say you have a wire between two telephone switches that can carry up to 10,000 simultaneous calls. Each circuit that is switched over this wire occupies one of those call slots. Thus, you can think of the wire as a resource that can be shared by up to 10,000 simultaneous users. The resource is divided up in a static way, even if you're the only call on the wire right now, and all other 9,999 slots are unused. Your circuit is still allocated the same fixed amount of bandwidth as when the wire is fully utilized. By contrast, the Internet shares network bandwidth dynamically. Senders push and jostle with each other to get their packets over the wire as quickly as possible, and the network switches decide which packet to send, i.e. the bandwidth allocation from one moment to the next. This approach has the downside of queuing, but the advantage is that it maximizes utilization of the wire. The wire has a fixed cost, so if you utilize it better, each byte you send over the wire is cheaper. A similar situation arises with CPUs. If you share each CPU core dynamically between several threads, one thread sometimes has to wait in the operating system's run queue while another thread is running, so a thread can be paused for varying lengths of time. However, this utilizes the hardware better than if you allocated a static number of CPU cycles to each thread. See response time guarantees on page 298. Better hardware utilization is also a significant motivation for using virtual machines. Latency guarantees are achievable in certain environments if resources are statically partitioned, for example dedicated hardware and exclusive bandwidth allocations. However, it comes at the cost of reduced utilization. In other words, it is more expensive. On the other hand, multi-tenancy with dynamic resource partitioning provides better utilization. So it is cheaper, but it has the downside of variable delays. Variable delays in networks are not a law of nature, but simply the result of a cost/benefit trade-off. Roman 4. Peering agreements between Internet service providers and the establishment of routes through the Border Gateway Protocol (BGP) bear closer resemblance to circuit switching than IP itself. At this level, it is possible to buy dedicated bandwidth. However, Internet routing operates at the level of networks, not individual connections between hosts, and at a much longer timescale. However, such quality of service is currently not enabled in multi-tenant data centers and public clouds, or when communicating via the Internet. Roman 4. Currently deployed technology does not allow us to make any guarantees about delays or reliability of the network. We have to assume that network congestion, queuing, and unbounded delays will happen. Consequently, there's no correct value for timeouts. They need to be determined experimentally. Unreliable clocks. Clocks and time are important. Applications depend on clocks in various ways to answer questions like the following. What's the 99th percentile response time of this service? How many queries per second did this service handle on average in the last 5 minutes? How long did the user spend on our site? At what date and time should the reminder email be sent? What is the timestamp on this error message in the log file? Examples 1-4 measure durations. For example, the time interval between a request being sent and a response being received, whereas examples 5-8 describe points in time events that occur on a particular date, at a particular time. In a distributed system, time is a tricky business because communication is not instantaneous. It takes time for a message to travel across the network from one machine to another. The time when a message is received is always later than the time when it is sent, but due to variable delays in the network, we don't know how much later. This fact sometimes makes it difficult to determine the order in which things happened when multiple machines are involved. Moreover, each machine on the network has its own clock, which is an actual hardware device, usually a quartz crystal oscillator. These devices are not perfectly accurate, so each machine has its own notion of time, which may be slightly faster or v. Although the clock is called real-time, it has nothing to do with real-time operating systems, as discussed in response time guarantees on page 298. Slower than on other machines. It is possible to synchronize clocks to some degree. The most commonly used mechanism is the Network Time Protocol (NTP), which allows the computer clock to be adjusted according to the time reported by a group of servers. The servers in turn get their time from a more accurate time source, such as a GPS receiver. Monotonic versus time-of-day clocks. Modern computers have at least two different kinds of clocks, a time-of-day clock and a monotonic clock. Although they both measure time, it is important to distinguish the two, since they serve different purposes. A time-of-day clock does what you intuitively expect of a clock. It returns the current date and time according to some calendar, also known as wall clock time. For example, Clock get time clock real time on Linux fin system. Current time millis in Java return the number of seconds or milliseconds since the epoch. Midnight UTC on January 1, 1970, according to the Gregorian calendar, not counting leap seconds. Some systems use other dates as their reference point. Time-of-day clocks are usually synchronized with NTP, which means that a timestamp from one machine ideally means the same as a timestamp on another machine. However, time-of-day clocks also have various oddities, as described in the next section. In particular, if the local clock is too far ahead of the NTP server, it may be forcibly reset and appear to jump back to a previous point in time. These jumps, as well as the fact that they often ignore leap seconds, make time-of-day clocks unsuitable for measuring elapsed time. Time-of-day clocks have also historically had quite a coarse-grained resolution, for example moving forward in steps of 10 ms on older Windows systems. On recent systems, this is less of a problem. A monotonic clock is suitable for measuring a duration time interval, such as a timeout or a service's response time. Clock get time clock monotonic on Linux and system. Nanotime in Java or monotonic clocks, for example. The name comes from the fact that they are guaranteed to always move forward, whereas a time-of-day clock may jump back in time. You can check the value of the monotonic clock at one point in time, do something, and then check the clock again at a later time. The difference between the two values tells you how much time elapsed between the two checks. However, the absolute value of the clock is meaningless. It might be the number of nanoseconds since the computer was started, or something similarly arbitrary. In particular, it makes no sense to compare monotonic clock values from two different computers, because they don't mean the same thing. On a server with multiple CPU sockets, there may be a separate timer per CPU, which is not necessarily synchronized with other CPUs. Operating systems compensate for any discrepancy and try to present a monotonic view of the clock to application threads, even as they are scheduled across different CPUs. However, it is wise to take this guarantee of monotonicity with a pinch of salt. NTP may adjust the frequency at which the monotonic clock moves forward. This is known as slewing the clock. If it detects that the computer's local quartz is moving faster or slower than the NTP server, by default, NTP allows the clock rate to be speeded up or slowed down by up to 0.05%, but NTP cannot cause the monotonic clock to jump forward or backward. The resolution of monotonic clocks is usually quite good. On most systems, they can measure time intervals in microseconds or less. In a distributed system, using a monotonic clock for measuring elapsed time, for example timeouts, is usually fine, because it doesn't assume any synchronization between different nodes' clocks and is not sensitive to slight inaccuracies of measurement. Clock synchronization and accuracy. Monotonic clocks don't need synchronization, but time-of-day clocks need to be set according to an NTP server or other external time source in order to be useful. Unfortunately, our methods for getting a clock to tell the correct time aren't nearly as reliable or accurate as you might hope. Hardware clocks and NTP can be fickle beasts. To give just a few examples, the quartz clock in a computer is not very accurate. It runs faster or slower than it should. Clock drift varies depending on the temperature of the machine. Google assumes a clock drift of 200 ppm parts per million for its servers, which is equivalent to 6 ms drift for a clock that is resynchronized with a server every 30 seconds, or 17 seconds drift for a clock that is resynchronized once a day. This drift limits the best possible accuracy you can achieve, even if everything is working correctly. If a computer's clock differs too much from an NTP server, it may refuse to synchronize, or the local clock will be forcibly reset. Any applications observing the time before and after this reset may see time go backward or suddenly jump forward. If a node is accidentally firewalled off from NTP servers, the misconfiguration may go unnoticed for some time. Anecdotal evidence suggests that this does happen in practice. NTP synchronization can only be as good as the network delay, so there is a limit to its accuracy when you're on a congested network with variable packet delays. One experiment showed that a minimum error of 35 ms is achievable when synchronizing over the internet, though occasional spikes in network delay lead to errors of around a second. Depending on the configuration, large network delays can cause the NTP client to give up entirely. Some NTP servers are wrong or misconfigured, reporting time that is off by hours. NTP clients are quite robust because they query several servers and ignore outliers. Nevertheless, it's somewhat worrying to bet the correctness of your systems on the time that you were told by a stranger on the internet. Leap seconds result in a minute that is 59 seconds or 61 seconds long, which messes up timing assumptions in systems that are not designed with leap seconds in mind. The fact that leap seconds have crashed many large systems shows how easy it is for incorrect assumptions about clocks to sneak into a system. The best way of handling leap seconds may be to make NTP servers lie. By performing the leap second adjustment gradually over the course of a day, this is known as smearing, although actual NTP server behavior varies in practice. In virtual machines, the hardware clock is virtualized, which raises additional challenges for applications that need accurate timekeeping. When a CPU core is shared between virtual machines, each VM is paused for tens of milliseconds while another VM is running. From an application's point of view, this pause manifests itself as the clock suddenly jumping forward. If you run software on devices that you don't fully control, for example mobile or embedded devices, you probably cannot trust the device's hardware clock at all. Some users deliberately set their hardware clock to an incorrect date and time, for example to circumvent timing limitations in games. As a result, the clock might be set to a time wildly in the past or the future. It is possible to achieve very good clock accuracy if you care about it sufficiently to invest significant resources. For example, the MiFID Roman II draft European regulation for financial institutions requires all high-frequency trading funds to synchronize their clocks to within 100 microseconds of UTC in order to help debug market anomalies such as flash crashes and to help detect market manipulation. Such accuracy can be achieved using GPS receivers, the Precision Time Protocol (PTP), and careful deployment and monitoring. However, it requires significant effort and expertise, and there are plenty of ways clock synchronization can go wrong. If your NTP daemon is misconfigured, or a firewall is blocking NTP traffic, the clock error due to drift can quickly become large.